Hello, I'm going to present a tensor model of the psyche based on social evidence and resource constraints. Most of the talk will be dedicated to the tensor model of the psyche, and in the very end, we'll discuss how it can be based on social evidence and resource constraints. In the most of the talk, I will be referring to some papers, earlier or recent papers provided by myself and colleagues, and the details can be found in the papers, while this talk will give just a brief overview of the findings and the conclusions and the ideas. Let's start from the definition of the general intelligence, because based on our approach, the psyche is kind of operating system for an intelligent agent, which is using intelligence as a decision-making subsystem of this psyche. According to joint definition of the general intelligence by Ben Gersel, Pei Wang, Shane Leck, and Marcus Hutter, intelligence is about reaching complex goals in different complex environments using limited resources. Let's take this definition apart and focus on reaching complex goals, complex environments, and consider that in order to reach these complex goals in these complex environments, an agent should execute some complex actions. And complexity starts from single goal that can be reached, single feeling or environment variable or a sensation which describes an environment, and a single action. So if an agent needs to reach one goal at a time based on certain single environment variable or sensation from the environment, and it can perform or not to perform single action at a time, we can describe the state of an agent in three-dimensional space of goals, actions, and environmental signals. However, in reality, the complex goal means that the goals may be counted, so we may have multiple goals at a time. Also, environments may be quite complex, so we may have different sensory inputs. And also we can perform multiple actions at a time. And also the structure of the goals may be complex, so there may be goals and sub-goals. Structure of the actions may be complex, so we may have higher level actions and lower level actions. And also environmental signals and sensations may have very complex structure, like there may be different channels. Each channels may have different dimensions and multiple sub-channels. So in this case, on each of these directions, we have not a single scalar value. On each of these dimensions, we may have not a single scalar value, but an entire vector. And so we have three vector spaces, which can be described by a tensor of second rank. And if the structure of the goal sections and environmental signals or sensations is also complex, it may be tensor of much greater rank. Now let's define the psyche. If an agent can be considered as a system operating in some outer world, where the world is kind of operational environment, then we can think that psyche is operating system of this agent. In this operating system, we have the decision-making system, which is agent's intelligence, and this decision-making system operates in the space, and that is space of states described or expressed in the tensor space, which we discussed on the previous slide. So we have sensations, which are obtained as perceptions of some outer environmental variables via agent's sensors. Then there are needs or goals that agent is supposed to reach based on its evolutionary destination or hard-coded policies or some goals that agent learns during its course of operations. And then there are actions that agents is about to execute or executes. The flow of operating of such operating system is like sensations are obtained from the sensors, then they are combined with the current needs of the agent, and based on the focus or importance of sensations accordingly to the current agent's needs, the emotional motivation is fed into the decision-making system, which is using either system 1 or system 2, where system 1 is kind of subconsciousness of an agent, or a fast thinking system accordingly to Daniel Kahneman, or agent can use conscious reasoning, which is system 2 or system of slow thinking accordingly to Daniel Kahneman, and the agent is making some decision, where decision combines expectations of what is supposed to happen next based on the agent's action or inactivity, and the action itself, what is going to be committed against the environment, so the expectations come true. When the expectations are created, the action is sent to the outer environment or outer world through the agent's actuators, and expectations are created so the agent expects something to happen. If we consider that each situation in agent's memory can be considered as a state, and if we want to simplify our discussion representing the complex tensor space of agent states by vectors, let's just combine the vector of sensations, the vector of needs, and the vector of actions into a unified vector S, which represents the current agent state. And let's say at time t-1, agent has certain sensations f t-1, needs y t-1, and actions a t-1, and based on these sensations, needs, and actions, agent makes some decisions and creates some expectations corresponding to these decisions. And then the expectation is moved to the present state. So agent expects a present state to appear, and then when the sensors are reporting the reality, like whether the actions has been actually executed, what is the current fulfillment of the needs or achievement of the goals, and what are the current sensations, the agent has ability to compare the planned expectations of the present and the reality, factual present or factual state of the present. And this comparison may be agent to adjust its behavioral model in order to make further decision-making process more accurate. And then it makes another expectation for the next time t+1. This has been discussed in our and presented in our paper with Vladimir Kryukov, which is referenced at the bottom of the slide. Based on this framework, we can define two different high-level functions, where one of them, function L, can be considered as a learning function, and function which is argmax of U and P is a function for decision making. The learning function operates on three arguments. First argument represents the vector of satisfaction of the needs or achievement of the goals. And it is based on vector difference between the previous state of need satisfaction and goal achievement and the current state. And the x is a weighting function. So the weighting function represents the priorities or importance of particular needs or goals in the agent midterm or long-term profile. So multiplication of the priority vector and the extent of the goal achievement and need satisfaction provides a first vector argument. Another vector argument is reality check. The reality check is a difference between the S prime, which is expectation at time t, and actual reality, actual state of an agent at the time t. And based on this difference, we provide the third argument. And the second argument, sorry. And the third argument is energy efficiency of the action performed at the previous state, which is reversed to the energy consumption of this action. This learning function may be used to actually learn the utility of the transition between the state at time t-1, actually not just state, but the series of states preceding time t, and the time t. What is interesting is that this utility function, representing the utility of the agent behavior expressed in terms of executing the action A, may be considered as a generic learning framework applicable for reinforcement learning and unsupervised learning. If we consider only the first argument, which is based on the extent of goals achievement and need satisfaction weighted by the agent profile function, we can consider that we perform the reinforcement learning, where the reinforcement is based on the vector of goal achievement and need satisfaction. If we focus only on the difference between the expectation and reality, we effectively perform unsupervised learning, where the loss function is based on the difference between the predicted token and the actual token. And the token can be considered as a state, and the previous sequence of tokens can be considered a previous series of states. So theoretically, if we tokenize the states and use conventional transformer operating on these states representing as tokens in a sequence of agent episodic memory, then we can consider this learning function L is a transformer learning function and the U is a transformer model. Similarly, if we consider the loss function is based on the need satisfaction and goal achievement, we use reinforcement learning based on transformers. Let's move to the decision-making function. The decision-making function is based on the utility model or utility mapping function, which we just discussed, and the probability function, where the probability of transitions between the series of states where the number of states is t and the next state after the series of states, that's just the probability or conditional probability of state at time t after the t large number of previous states. And then different combination of the utility function and probability function can be used to make a decision and select the next state where the action to be executed is a vector being part of the expected state. In this case, we can consider decision-making process as an operation risk management problem. Let's consider the example on this slide. Let's say we are at the state S1, and at the state S1 we can perform four different actions. Action 1, which can lead to S2 and S3 depending to different conditions or environments that are beyond of our control, and respectively in state 2 after the action 1 will have a goal satisfaction or need satisfaction or goal achievement y1, and in case of state 3 we'll have goal achievement and need satisfaction y2. So if we do a1, we can get in either in s2 or s3 with y1 and y2 respectively. In both, and the probabilities are equal. So p is a probability. So with equal probability after a1 we can get into s2 or s3, but based on the y1 and y2 the utility of the new state will be different. S2 will have utility of 1.0 and S3 will have utility of 0.4. Similarly, if we commit action A2, we can get into the state either S4 or S5 with respective satisfaction of the goals Y3 or Y4, with utilities 1.0 in case of Y3 and no any utility of state 5 with state of the need satisfaction y4. But the probabilities will be different. So getting into S4 has sufficiently larger probability 0.8 than getting into S5 with probability 0.2. And then if we commit action A3 or A4, we can get respectively to S6 or S7 states, which will correspond to need satisfaction Y5 or Y6, where the utility will be either 0.6 or 0. But the probability will be 1.0, so A3 unconditionally leads to S6, while A4 unconditionally leads to S7. So only A1 and A2 lead to some stochastic unpredictable output with two different options with different probabilities and different utilities. So based on that, we can compute the example different. We can consider different strategies for decision making. One strategy would be just sum up the utilities and probabilities, multiplication of utilities and probabilities of each outcome based on the common action. So for action A1 it will be 0.7 and for A2 it will be 0.8. And for A3 and A4 it will be simple because there is no any probabilistic distribution of the outcomes. And what we find is that from the point of view of rational selection based on risk management policy, the most optimal solution is A2, because even though there is a chance of getting no any utility in case of S5, still the utility and probability, joint utility and probability of S4 is great enough, so the overall usefulness of the action 2 is greater than overall combined utility times probability summed up for action A1. Well, interestingly, the theory of perspectives by Tversky and Kahneman says that most people behave non-rationally. Most of the people would select action 3 because action 3 corresponds to predictable output. The utility is small, but the outcome is predictable. So for sure, person is getting some outcome that is higher than the worst scenario in case of action A2 or the worst case of the action A1. When we discuss the structure and space of the needs or goals, or they can also be considered as values or missions, we hardly can think about some pyramid like the hierarchy of needs according to Maslow. In fact, we can deal with some space where needs and goals vary from psychological on one end and physical or physiological on another case. Or on another dimension, they become varying from being existential, like lifelong, or routine, like every day. And it is important to note that there is no single need or goal for an agent to be satisfied at the current moment of time. In general, it might be some complex vector of different goals or needs scattered over this space, weighted by the x functions, which corresponds to the agent profile. So different combinations of goals with different weights may describe the personal profile of an agent, of every agent being a human or theoretically artificial agent, and over the lifetime the priorities of an agent may change. Another important note is that practically we can hardly make a sharp difference between the different state variables that we separate into actions and to needs and the sensations. At some point, we can consider that there is something which is more like a need or value, which is long-term and existential, like giving a birth to next generations. And there is something more short-term or transient, which is like get married. And then going down from the top of hierarchy to more specific goals, sub-goals, we go down to specific tasks, which are getting down to specific subtasks, and then these specific subtasks get into the actions and potentially sub-actions. So in order to give a birth to next generations, we need to get married. In order to get married, we need to make a marriage offer, which is sequence of making the visit and spelling the word to the person who we are going to marry. In order to make the visit, we need to reach the house, climb the stairs, knock at the door, and in order to reach the house, we need to make steps from the front door. And in order to make every step, we need to bend the knee and straighten a leg on each step, and this brings the whole hierarchy of needs, values, goals, tasks, goals, sub-goals, tasks, subtasks, where each of them can be considered as a goal at certain level of the behavioral hierarchy. Another example is that which represents the complex structure and interdependency between the state variables corresponding to the feelings or sensations, the needs or goals, and the decided and committed actions, is that they are conditioning each other. And they are conditioning each other on both on vertical axis, like getting resources is more high level than making a step, and stretching a leg and bending a knee is more low level than making a step. And at the same time, getting resources as a task corresponds to replenishing resources as a goal or a need. On the other hand, we have another need or a goal to conserve resources, and replenishing resources and conserving resources are kind of contradicting each other, because in order to replenish resources we need to avoid conserving resources, and if we want to conserve resources, that inhibits replenishing resources. And since replenishing resources involves or causes getting resources activity, and getting resources activity inhibits conserving resources goal, there is some positive and negative connections between each of the state variables. Similarly, we can consider dependency on the feelings, like we have higher order feelings and lower level feelings, and these different feelings may have different dependencies to the satisfaction of the needs. In order to describe that, in order to describe the state space of an agent, we can use two different approaches, which are traditionally two different perspectives for artificial intelligence. One of them is subsymbolic or associative, which has been handled by modern neural networks, which are described by tensors. Another approach is so-called symbolic, which is expressed by graphs or in complex cases by hypergraphs. Interestingly, the latest work written by Pedro Domingos last year presents the formalism which makes it possible to use the same language to describe any models, being either symbolic or subsymbolic. So using the same formal language, we can describe any neural network models or any probabilistic or plain logical graph reasoning models. That goes in line with the concept of two different systems presented by Daniel Kahneman, where we have a system one for fast associative thinking and system two for slow logical thinking, where the subsymbolic knowledge in a neural network may be described by a dense non-labeled graph or parameters of a multi-layer neural network. And the same model can be described by the graph representation, where the different nodes correspond to either symbols indicating certain categories or properties, or logical disjunctive or conjunctive operations on these symbols or the other operations hierarchically. Moreover, in probabilistic logical networks like PLN or NARS or discovery system being developed by Evgeny Vityaev, the connections on the symbolic graphs may be non-binary and expressed by some probability measures like Bayesian probabilities. And what is nice with that tensor logic presented by Pedro Domingos is that the structure of the tensors, no matter whether this structure describes dense neural networks of any architecture or arbitrary probabilistic or logical networks, symbolic logical networks, the vertices of the graph may be represented by different probability descriptions or logical descriptions. In the simplex case, in every point in this tensor space described by tensor logic, we may have just Boolean values. And then that would describe just Boolean logic. For instance, if we want to build the knowledge base to classify the animals, and if we know that all horses are striped, like every horse is a zebra, then we just have the striped horse value as Boolean and say it's true. If we rather think that the horses are not striped, we set it to false. So the horses may be either striped or not striped, which is not true in general, as we know. If we consider probabilistic artificial neural network or Bayesian logic or just trained neural network for horse predictions, we find that based on the distribution of the horses on the planet, the probability of a horse to be striped is 1%, given the number of zebras and the amount of all horses that are non-zebras on the planet. And then that would be the weight in the same node or the same graph vertex in a neural network or the logic-based and logical network corresponding to stripedness of the horse. However, if we want to have a more accurate account for evidence and probability as well, in the same node on the graph, either neural network graph or plain symbolic graph, we can have the whole record of evidence, like number of striped horses versus number of actual horses, including the striped horses, and then get the accurate estimation of the probability. And while the model is learning, we can add numbers to both sides of this formula or complex number on the graph. And we can avoid overfitting, and we can avoid catastrophic forgetting or catastrophic remembering within the scope of the whole model. Now let's talk about the problem associated with the space. The amount of state variables in terms of the needs, in terms of the actions, and especially in terms of the feelings or sensations for any intelligent agent is enormous. And the domination of the dimensionality is a problem that we need to solve. And the way to solve this problem is dimensionality reduction and the increase of discreteness. For instance, if we are going to optimize the structure of the knowledge for storing some inventory in a store for different sorts of trousers, we can disregard the length and we can disregard the pockets, and we can just eliminate some of the properties that are not important for customers. Moreover, we can consider that we don't need to focus on the waist size, and we can just redefine the dimension or indicating property such as waist size and redefine it as a size, with sizes being either large or medium or small. We can also consider that the property corresponding to the kind of the good, like trousers, breeches, and shorts, can be rescaled down to just two different symbolic values, like being either longs or shorts. And finally, one of the dimensions, such as a gender, being a male or female, can be just kept. Anyway, during this operation, we reduce the dimensionality from 5 to 3, and we increase the discreteness of two dimensions, such as waist and the kind. What is important is that dimensionality reduction is not just physical. It's not just about the compression of the data. Importantly, it is compression with the loss. So when we compress the data, we eliminate what we don't need, and we remove accuracy that we don't need in operations in order to save the resources. Remember, in the beginning of the talk, we have defined the definition of the intelligence, where an agent should deal with complex goals in complex environments given the limited resources. And remember that our utility function is learned based on the energy efficiency. So the more energy we save and the less energy we spend in order to reach the same level of goal achievement and need satisfaction and have the same level of the expectedness of our activity, the greater the utility function. So the energy efficiency is one of the ingredients of the input for utility function being learned. In order to do that, we need to be mindful about the practical use of our compression procedure. For instance, if we are interested about meeting the young ladies, then given this particular picture, we need to be compressing this picture down to the two-dimensional space, saying about the experience of some young female person. If we are rather concerned about the care about senior citizens, if we are going to take care about senior gentlemen and ladies, then we rather perceive this picture as an image of an old female. Again, we reduce the whole information and the pixels and the vectors of this image down just to one point on two-dimensional space, saying that we see either old female or young female woman, dramatically compressing the information. And the compression of the information is happening with loss, so we forget the entire the arrangement of the pixels and strokes on this picture, but we keep the focus and the meaning of the information. Another example, referring to the some experimental results that I will show in a few minutes, is about the reduction of the dimensionality and the increase of the decrements in the case of some video game, where we redefine five-dimensional input of RGB pixels on two-dimensional space, first to grayscale image on two-dimensional space, and then to just horizontal position of the ball and horizontal position of the racket on some highly discrete space, and then finally getting it down just to horizontal differences between the positions of the ball and the racket at two different moments of time with much greater discreteness. What is interesting is that our research committed 3 years ago on structure of the human languages, namely English, Russian, and Chinese, has shown that the entire structure of the lexicons of these three languages is effectively a matter of compressing the information being committed using these languages as a communication codes. What we have done, we have tried to perform different tokenizations of the unsupervised tokenizations of the English, Russian, and Chinese texts without of the prior knowledge, without of any prior knowledge about the punctuation and letters in either of the language. And we were trying to build tokenization models based on the same approach that I have just presented on the few slides ago. We disregarded the energy efficiency component, we disregarded the goal satisfaction component, we considered only the expectation component, and we have built the probability conditional probability graphs. And based on these conditional probability graphs, we have tried different tokenizations, the unsupervised tokenization techniques. And based on different hyperparameters of these tokenizations, we have found that the f-scores of these tokenizations, where the f-scores are all on vertical axis of these slides, are corresponding to the semi-linearly corresponding to anti-entropy, compression factor, and predictive power of the models built for these tokenizations. So let me explain what we see on these slides. On the vertical row, we see the English, on the middle row, we see the Russian, and in the bottom row, we see the Chinese. So we see English at the top, Russian in the middle, and Chinese at the bottom. On the right and the left blocks, we see results for different corpora. Like on the left, we see different corpora with 1000 texts, and on the right, we see 100 text corpora for the same three languages. And in each row, in each block, or left or right, on the vertical axis, we see F-score of the tokenization process. And on the horizontal axis, we see different parameters which are evaluated based on the tokenization. First, it is anti-entropy, and it is in the function inverse to Shannon's entropy. Next is the just compression factor. It's just ratio of compression based on the tokens as a lexicon entries. If you consider the tokens tokenization is just process of compressing the text down based on the dictionary of the tokens and the entries of these dictionary entries through the sequence, replacing these indexes instead of the sequences of letters. And cross split F-score is over average F-score based on the two different splits, where we train the model to do tokenization on one split and then evaluate F-score of tokenization accuracy on the other split, and the other way around on two different splits. And the third metric compared against F-score is just combined indicator of anti-entropy, compression factor, and cross-split F-score. So what we see that for English and Russian and for Chinese, the correlation between the each of these metrics and the F-score is semi-linear. And it is interesting that linearity corresponds to the amount of characters in the lexicon, the smallest number of characters in the in alphabet, the smaller number of characters in the alphabet in the English. So in most of the for most of the parameters and for both corpora, the correlations are semi-linear. For Russian, it is a little bit more scattered, and for Chinese and in Russian we have more symbols in the alphabet, and for Chinese it's the greatest. It is scattered to greater extent. But what is interesting that the linear connection between these metrics depends on the corpora size. So we have run you can see that the linear correlation is seen more clearly for 1000 Chinese corpora than in case of 100 Chinese corpora. And we have some other slide where we explore this correlation and distribution on different sizes of Chinese corpora, and we can get it more and more linear when the corpora size increases. So let's go to some practical experiments. One experiment that we were trying to run using our model is a virtual game in an environment provided by OpenAI Gym. In particular, we use an Atari breakout game where we have the model of the game where you need to use a pedal or a rocket or a racket to control the ball, and the ball, your goal is to reflect the ball so it hits the opposite wall and destroy the bricks on the top. And we have some policy of computing the reward or feedback rules to provide reinforcement to the model, where the reward and feedback rules correspond to evaluation of certain goals or needs being defined by the nature of the game. And then we can learn the utility and probability as model and policy, and based on the learned model we can perform certain actions like moving left, moving right, or firing the ball. And the model we have is implemented. We it was made based on the state series or sequences of states transition to a new states, like we described on the previous slides. And the learning has been performed by what we call global feedback, which is described in the reference paper. Shortly, it is like you memorize the certain meaningful episodes, like sequence of states between certain psychologically valuable moment, like either winning a game or losing a ball, or getting a reward because of hitting the brick, or losing the life because a ball is getting down on the floor. And based on the whole segments of these meaningful episodes of episodic memory, we provide the either positive or negative feedback for entire episode at the end of the episode. And when we provide the positive or negative feedback for entire episode, all transitions that are part of this episode are reinforced. What is interesting is that we have tried to learn behavior within such a model in two different experiment setups. First experiment setup was based on so-called discrete representation of the space of states, and that means that we were just considering pixels. So what was fed into the input was just about the pixels, and the pixels were corresponding to the position of the racket or the ball just by means of being pixels either colored or not. And another experimental setup was based on so-called functional model, where we have reduced the dimensionality of the input space from the pixels to the positions of the ball and the racket, like I have shown on one of the previous slides. And the learning framework was the same as I discussed it ago. It's only the structure and content of the states of space was different. In first case, the input feelings or sensations were about the colors of the pixels, and in other case it was about the positions of the ball and the racket. And what is interesting is that both models made it possible for us to learn the meaningful behavior and to provide the ability to learn the game with the same amount of learning steps, no matter which experimental setup was involved. But as we would expect, the discrete setup with pixels was much more resource and time consuming than setup based on the functional representation with coordinates of the ball and the racket. So we conclude that if we apply the one of the inputs of the grand utility function, then the utility function, which is able to minimize energy and resource consumption, reducing the dimensionality down to the less expensive environment, computationally less expensive environment, this function appears more useful in the end, having greater utility. Here are the results of our work. These results are based on the Atari OpenAI Gym breakout game. So we were able to reach level of performance comparable to or exceeding the average human level, comparable to the level reached by deep Q-learning network, and even exceeding the top level of deep Q-learning network. And what we have found is that if we normalize our results based on the number of learning frames, we are able to get greater performance at the lower number of steps compared to previous results provided by deep Q-learning and Rainbow IQN algorithms. Finally, let's move to the another part of advertised topic about social evidence and resource constraints. So let's think that for an agents that are part of the social environment, for an agents which consume most of the inputs not from the environment but from other peers, from other humans, or from news media, or from some books or reports, or whatever paper or electronic information sources, the need to evaluate the trust level of trust to the information perceived by the agent in order to make decision, or just in order to evaluate the reliability or confidence of certain information that is needed to make certain decision at some point. It is it is critically important. So in order to make decisions, agents should maintain not only the information about the objects, about the events, and about the relationships between them. The agents should also maintain the information about the people or social media sources or whatever sources that provide such information, so the people can assess the trustability and reliability of this information. And the model that we have created in order to deal with this about 10 years ago and we were developing over the last 10 years deals with it within the concept based on 4 different graphs. So in order to deal with the information or state variables describing the socially relevant information in the agent's states of space, or in the agent's states, we can split this information in 4 different graphs. First of all, we have something what we call foundation graph, which is the part of the agent's model which describes unconditional truths of the agent's belief system. Let's consider example of the drinks preferred by an agent based on his or her social connections. So unconditional truths of belief system of an agent is just there are some drinks like beer, coffee, and tea, and these drinks are just drinks. So that's something that doesn't deserve any discussion. Then the agent has some social network in agent's mind. Like there is a Mary who is the best friend, there is a Peter who is just friend, and there is just some Bob who is just Peter's friend. And that's the social graph, which also records the levels of trust within the agent's mind. And then there is some situation described by some situational awareness, where Bob says that he prefers beer, Mary says that beer is not good, Mary says that juice is good, and so forth. So every person, when friends are coming into some bar, are expressing different opinions in respect to what to order. And then the agent, say myself, who is one of these friends, is making some inference. It might be implicit inference made by system 1, or it may be explicit inference made by some logical thinking. But this way or another, I connect the knowledge that is just basic, my social network, and my preferences to my friends, and the preferences of my own friends, in order to conclude that I would like order juice, maybe tea, at the very least sort coffee, and I won't try beer because of the preferences of my friends and their opinions, and my preferences in respect to my friends. And we have created the formal mathematical model for this kind of socially aware recommendation computation, and we can show within the paper that we have published in this year, here is the paper referenced, that this model can be used to explain not only the behavior or decision-making process of a person. It can also explain multiple phenomena, behavioral phenomena known to cognitive psychology or applied social psychology, like phenomena described by Robert Cialdini in his books on psychology of influence. Moreover, we can use this system in order to design artificial agents or psyches of artificial agents, which would be aligned with the interests and preferences of the people who are surrounding these agents. On the other hand, we can build the simulation systems which simulate the behavior of the whole human communities. In order to illustrate this and validate the reliability of our model, we have performed some simulation, which can be illustrated by this slide. So what we have created, we created population of 5 different agents, and initially each of these agents was given certain belief system, and the items in the belief system were denoted by letters A, B, C, X, Z, Y, X, Y, and C, and these letters correspond to some leisure activities or hobbies of the people. So let's say people who are having different hobbies, based on the similarity in their hobbies, form some structures. So let's say we have a social structure of agents at the top who share the A and activities A and B, and we have another structure of agents at the bottom who share the activity X. And let's start some communications. And let's say they perform communications given the model that I have described above, but in account with one more part of this model, which I forgot to mention when I was discussing this, and that's another important piece corresponding to initial definition that we have seen on the first slide. Remember, given limited resources, term suggested by Pei Wang. So whenever we make some inference or make some decisions or try to evaluate reliability or trustability for certain facts, we need to be mindful about the time that we have allocated to make this decision and the resources we have to do this kind of inference. That means that if we are limited in terms of the time and computing power, we may not consider all options, but we consider only the options that are highly relevant and highly aligned with our belief system, or that are corresponding to the most reliable social connections. So that means, for instance, if we cannot evaluate all items that we can consider that we have on the table, then we consider only the ones that are coming from our best friends or the ones that are most aligned to our ground beliefs or unconditional truths present in our mind. On the other hand, if we have a lot of social connections with a great level of trust, and if we still want to evaluate all possible options that we have on the table, we may not have a cognitive ability to consider all of them, and we retain only those of them who get the highest probability and highest assessment in terms of our social peers and highly aligned with our belief system, and we disregard what doesn't fit our inference engine. And then what happens in the course of such interaction is that the agents who are closer to each other, they may be getting more and more closer. And the agents who are further away from each other may be getting further away from each other over time, unless there are common values that are joining them together. Like in this example, in the beginning of the interaction, agent in the middle is communicating a message with the value of some concept C to everyone here. So agent in the middle is broadcasting C to all agents around, and agent on the left bottom is messaging concept Z to everyone around, to their social peers. But what happens after this interaction is, due to the social proximities and social similarities on social connectivity between the agents, the message about Z communicated from this agent to this agent, it might get not that important to him or to her. And respectively, the message about C communicated by middle agent to bottom agents may not get that important to them as X, Y, and Z, where the agent, this agent perceives Z to great extent because of the large social proximity between these two agents. And over the time, if these small and low value Z and C are not reinforced by other ways, they may get forgotten, and because of the social distance after this first round of communications between the communities of agents is increased, the message B sent from middle agent to bottom agents and message Y sent from bottom agent to the middle agent may just get not delivered, or may get disregarded, or may get ignored, and over time we find just population of the agents who share only the unique sets of values. Like agents at the bottom may just keep X, Y, and Z, and the agents at the top may keep just A, B, and C in their belief systems, and some remnants of X, which can be get forgotten on the next step. So that just kind of qualitative experiment we have presented on this slide, but we have also run a quantitative simulation of the same population. And in the first round of simulation, we created a population of agents with the distribution of beliefs like I described on the previous slide. And the agents were limited in their social capacity. So they were limited in perception of the non-highly connected social peers, but all of the agents were quite cognitively capable. So they were able to perceive a lot of information, but from a smaller and restrictive amount of social channels. So what we see on the top? On the top, we see the structure of the agent's belief. Like agents are on vertical axis on the rows, and belief items are on the bottom or in columns. So agents A and B have both, agents 1, 2, and 3 all have A and B. The agents number 3 also has C and X. Agent 4 has X, Y, and Z, and agent 5 has 1 and X and Y. So here is the structure of the beliefs. And at the bottom, we have respective metrics of agent to agent proximities or belief proximities. So like agents 1 and 2 are quite similar, and here's the distribution of similarities between the agents. And from left to right, we see the social dynamics, different stages of social dynamics after the agent-to-agent broadcasting rounds. Like first round of broadcasting, after the second round of broadcasting, and after the third round of broadcasting. So what we see, as we would expect by the discussion on the previous slide, if the agents are socially limited and have limited social tolerance but large cognitive capabilities, they separate into two different distinct clusters. Like we get one cluster of the agents which are similar each to other, agents 1, 2, 3, and another cluster of the agents similar to each other, agents 5 and 4. And in the second cluster of agents, they all believe in X and Y and a little into Z. And in the first cluster, all agents believe in Y, in A and B, and a little bit into C and X. If we consider another simulation with the same starting point, but consider that the agents are rather socially capable, but cognitively limited, so they barely comprehend information that is not aligned with their belief, and they have limited capacity to handle low confidence information. Then, after the same broadcasting sessions, or stage, we see the convergence of the agent community to total uniform similarity. So everyone becomes similar each to other, and they all end up believing in the same number of values, where the number of values is limited. So everyone of them believes in X, and to lesser extent, less of them believe in X, and still some of one believe and to little extent they believe in A and B. What is interesting, during this experiment, we also confirmed the known so-called recency phenomena, where the greatest importance in a group communications is given to the participants of the group communications who speaks the last. Like if many people discuss something, and if they end up with some joint decision, then under other equal conditions, the consensus is biased towards the opinions of the people who speaks the last. So here we were running the communications in the agents from agents 1 to agent 2, and then to agent 3, and then to agent 2, 4, then to agent 5. To agents we were speaking in the order corresponding to the number of the agent, and respectively we see that the most valuable belief item and the most trusted belief item is found to be belonging to the agents initially sitting in the first cluster. If we change the experiment so the agent 5 speaks first, and then order of speaking goes back to the agent 1, then the pattern is different. So the greatest value of the belief items is given to the agents is given to the belief items A and B that belong to the agents 1, 2, and 3. Thank you for attention. If you are interested in the details of this work, please see the references provided in this presentation, and see the recording of the workshop on the subject and our paper on the New Informatics 2025 conference last year. Thank you.